Again, it's a rich thing.
What is going on, guys? Welcome back. In this second episode of the C programming tutorial for beginners, we're going to talk about data types and variables. So let us get right into it. So we're going to start by defining the basic structure of the code again, like we learned in the last video. We're going to include stdio, which is for standard input-output header file. And we're going to define a main function, the entry point of the program. And we're going to again return 0. Now, we're going to talk about variables and data types today, and a variable is essentially just a placeholder for a value. Now, if you are already familiar with Python, for example, in Python we have variables, but we don't have to specify the data type. So in Python, what I can do is I can just say a equals 10, for example, and that's it. I have now an integer, or I can say, I don't know, my text equals hello world, and that's it. So I don't have to specify a data type. I don't need to do anything manually. In C, if I want to specify, or if I want to create a variable that stores integers, I need to specify that this variable stores integers. So I need to say int a equals 10, for example. Or I can also just say int b without assigning a value. So this would mean that b is essentially just defined but not assigned. So b is whatever it is, but it's not. It doesn't have a specific value assigned. And this is how you do it essentially in C. And we have different data types with different sizes and with different minimums and maximums and so on. So this is what we're going to talk about in today's video. What we can do here right away is we can say b equals 20. And then we can go ahead, for example, and say int c equals a plus b. And now whenever I use c or a or b, this refers to the value behind that variable. So if I go ahead and say, if I go ahead and say printf and then %d plus %d equals %d, remember this is the placeholder that we learned about in the last video, then a \n here for the new line in the end, and I pass a, b, and c. What happens is that the first placeholder is filled with A, the second one is filled with B, the third one with C, and the result is obviously 10 plus 20 equals 30. So let me open a terminal down here and let's go to, we are already at the desktop, so gcc again, main.c. So we're compiling, the output is going to be main, and in order to run this now, /main, and you can see 10 plus 20 equals 30. This is what we printed. So this is very basic. I think we can also, I'm not sure if this is possible, but I think we should also be able to do it like that. Let's see. Maybe not, maybe yes. So gives me a warning. Okay, sec fault. So we need to use a placeholder. We need to say %d \n like that. We can just print the individual numbers as well. But we can use now these variables, and of course they can change the value. So I can go down here and say a equals 30 now, and then the results are going to be quite different. There you go. So you can see 30 plus 20 is 30, but this is of course not right because C was calculated when a was 10. So I can also take this line and put it down here, and then we're going to get the proper result. However, we're not going to talk about calculations here. What I want to talk about is the data type integer. And it's important to understand that different data types have different sizes. For example, the integer is defined to have at least 2 bytes. Now, why at least? Because in C, and we're going to have this pattern a lot of things are undefined. The size of an integer is undefined. I mean, not completely undefined, but it depends on the operating system. We know that it has to be at minimum 2 bytes. And I think that it's even defined as not 2 bytes, but 2 times whatever a char is, a character. This is another data type that we're going to talk about. And usually a character has 1 byte, which means that an integer has at least 2 bytes because 2 times whatever the character has, 2 size of the characters. But essentially, it can also be 8. Doesn't matter. So depending on the operating system, you're going to have different results. We can see what size an integer has by just printing it. So we can say print f, and then we can use here the placeholder again. And what we want to have here is we want to have size of. This is a function we can call size of a, for example. And this is going to give us the size of the variable a, so the size of the integer a. And if we want to format it into our output, we need to this time use ld, not d. Why do we need to use ld? Because the result of size of is actually a long integer. We're going to talk about longs in a second here. I need to define c because I undefined it. So as you can see now here, I get 4. This means that in our case, the integer has 4 bytes, or 4 times what a character has. And a character in this case has 1 byte on my system. So this is the size. What we can also do is we can see, okay, how much can I store with those 4 bytes? Because if I go ahead and say int, let's make another one. Let's say int d equals something like that. I think this should still be in the range. So I can just go ahead and say printf, then %d \n, and then d. This should not be a problem. There you go. But if I go too far, if I choose something like that, first of all, you can see here that I get a warning from my checking tool here from clang. And you can also see when I compile, I get this warning, and I can still run this, but I don't get the number that I have here. Why is that? Because we have a certain maximum and a certain minimum that we can display here, or that we can store in an integer. And this maximum and minimum can be seen by using a library, by including a library called, you can include the library called limits.h. This allows us to get the limits. And what we can do here is we can just go ahead and say printf int max value like that. And it's going to be %d \n. Don't forget that. And now we can access this value int underscore max. This is a value that we get from the limits.h. And I can copy this now and I can change the max to min. And I can print the int min value. So I can compile this, and now you can see what range I have when I use, let me just resize this here, what range I have when I use integers. So the max value I can store with an integer is this value. So I can go ahead now, uncomment this line, and I can change this value to 21474836647. And if I now go ahead and say printf %d \n d, there you go. If I do it, you can see that I can display this value, but what happens if I add one more? So what happens if I increase this by 1? What you can see now, first of all, you can see I got the warning again, and if I run this, you can see that I get the negative number, I get the minimum. So it basically overflows and goes full circle. So if I go beyond the maximum, it goes to the minimum again. So that's what happens here. This is what you can store with an integer. Now, if you don't need that range because you know that you're going to store smaller numbers, what you can use is you can use the short. So a short is basically an integer, but it's less than what an integer is capable of. But again, remember, this is a minimum. So in this case, you're going to see in my system, it doesn't make a difference because a short is defined to be a minimum of 2 bytes as well. Now, an integer is usually 4 bytes. A short is at least 2 bytes and usually 2 bytes. But as far as I know, I think at least that on my system, it's still going to have 4 bytes. This depends. This is undefined. This depends on your system. But if I say short s or short d equals, I don't know, 500, for example, we can go ahead and print the size of this short. So size of d in this case. I'm not going to say it. I know what you're thinking. Oh, actually, you can see that short in my system is 2 bytes. So I was wrong about this. This is also what is usually the case with 64-bit systems. Integers usually have 4 bytes, even though they're defined as a minimum 2 byte. Even though I'm not sure, I may be on a 64-bit operating system, integers have to be at least 4 bytes. But shorts have to be at least 2 bytes, and in this case, a short is 2 byte. If we want to see what the ranges here are, we can just copy that, and we can type shrt max and shrt min. And here I change this to short, compile, run. So those are the numbers. This is the range that we can use when we work with short values. Now, on the other hand, maybe you don't need less, but you need more. What you can do in this case is you can use a long. So you can just go ahead and say long e equals and then some large number. And then you can just print that. So you can say print. Now here you need to use LD, because if you want to display a long integer, you need to specify LD, not just D. Then again, \n, and in this case, E. And we can also print the size. Now, I can mention right away that there's not only long, but there's also long. So this is something that was introduced in a later standard, but you can also say long, F, for example. Now, I think this was where I didn't have a difference. So if I now print also F, and we also decide to print the sizes, so I'm going to print size long and size long. I think that on my system, they're going to be the same. What is here? Oh, here I think we need to add another L. Or actually for the size, not. We need to add another L here. So if you want to display a long, you need to specify LLD. And here we need to specify the size of E, size of F. And I think they should be the same here. There you go. They're both 8 bytes. Now, a long, as far as I noted here, a long has to have a minimum of 6 bytes. A long has to have a minimum of 8 bytes. In this case, a long also has 8 bytes. Doesn't have to be the case. In this case, it is the case. So on this particular system, it wouldn't make a difference. However, if I want to compile this code for many systems, I should use long if I want to use the full range. Now, if you want to see the range, again, what we can do is we can just copy this here. Come on, undo. You can copy this here, go down here and replace short by long. So we can, let's just look at the maximum value. So long max and long max. And here we're going to say long max and L long max. And of course, here we need to also specify LD and LLD. Those are just placeholders. There's not really a logic behind this. It's just long. I'm not sure what D stands for. I think decimal maybe, or something representing a number. And LL means long, obviously. So if I go down here and I compile this now, you can see those are the maximum values. Now in this case, it gives me the same value. Usually it's not the case. It's just the case on this particular system. Usually a long has to store at least 6 bytes, so it would be less. If you want to calculate this yourself, you can also go into the calculator and on Windows, for example, and you can go to programmer and you can type here into the binary. 1 byte is 8 bits. So if you have, if you have something like that, this would be 1 byte, and this would be 2 bytes, this would be 3 bytes, this would be 4 bytes, and this is what you can store with that. So essentially you can use this to find out what you can store. Now, maybe you say that you want to use 4 bytes, but you don't need negative numbers. So instead of going for more bytes, what you can do is you can make the variable unsigned. Now, by default, every variable is signed. So if I define int, it's the same as saying signed int. And what this means is that the 4 bytes are used for negative values and for positive values. So half of the bytes are used for negative values and half of the bytes are used for positive values. Which means that I can store from this number up until this number. Now, maybe I say I don't need negative numbers, but 4 bytes are enough because I just need this and twice as much. So what I can do here is I can say unsigned int, and let's call this now G. I can say unsigned int G equals, and then we can go for a number that is higher than that. So let's copy this, let's paste this here, and let's increment this. a couple of times. So let's go for 9,000 increments. There you go. Did this with Vim right now. And I can still represent that number. I can also change this here to 5, for example, and this here to 3. And then I can go ahead and say printf d\n. Now I need to say ud for unsigned, and then g. This is important. When you want to print an unsigned integer, you need to specify ud, not just d. There you go. Or actually, oh, sorry, it was only u. It was not ud, it was only u, because that is unsigned already. There you go. So now it works. Now, if you want to do the same thing with a long, what you need to do is you need to say lu. So if you want to do this with a long integer, by the way, saying long int and just long is the same thing. So if I want to do this like that, I can also do this. And if I want to see the limits here, all I need to do is I need to say printf, and I'm just going to do this now for unsigned long, so that we don't have to go through all the examples. Unsigned long maximum, and this is going to be an LLU, or let's go for long maximum, and \n. What we have here is ull ong max. This is the thing that we get from the limits library again. So I can compile, I can run. This is the maximum value that we can have with an unsigned long. And of course, the minimum value is 0, so we cannot go into the negatives. All right, so let us continue with the floating point numbers. I deleted all the code that we have up until now. And what we can do here is we can specify a float variable. So the data type float is for floating point numbers, f1. And this data type has a minimum of 4 bytes as far as I know, and it has 6 decimal places of precision. So if I say f1 equals 12.3456789 and continue the pattern 1, 2, 3, 4, 5, 6, 7, 8, 9, for example, we can write that, but the precision is limited. So first of all, we can print that the placeholder is %f \n f1. There you go. So there you go. There you go. You can see, first of all, it's not printed fully, but even if I specify how many places I want to print, I can do that by saying point and then, for example, 20 to see 20 decimal places. Even if I do that, you can see that the precision is not enough. 1, 2, 3, 4, 5, 6, and then it doesn't say 8, it says 9, 2, 8, 3. It's not precise anymore. So a precision of 6 decimal places means that it doesn't matter where the point is. So even if I remove this here and I say, I mean, I don't know if it's completely irrelevant, but if I say something like that, for example, there you go, you can see that still the pattern breaks pretty soon. So we have 1, 2, 3, 4, 5, 6, 7, 8, and then 0, 6, 2. The pattern does not continue. So the precision is limited. If we want to have more precision, by the way, let me just print the size here. Printf size of f1 is going to be ld \n size of f1. And what you see here is 4 bytes. All right. So if we want to have additional precision, what we can do is we can use doubles. So a double has double precision. It has 15 decimal places of precision. It has 8 bytes minimum. So D1 could be 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's the same number actually, but we're going to have a higher level of precision. So we can copy that, we can paste this, we can change this to D, we can change this to D, and we can change this to D. And now you can see that we have the same number, but this one has more precision for a longer time. So here we already break the pattern here, and here we continue on up until there. So it has more precision, and it also takes twice as many bytes of space. We can also take a look at the limits here, but it's not contained in the limits h. It's contained in I think it was float h. There you go. And here we can then just say printf max float %f, and the max float that we can represent is flt max. And I think we should also have something for the double. I think so, at least. dbl max. And we should probably work with \n here. There you go. So the max float is this, and the max double that we can represent is this. But keep in mind, there is a precision limit. So this has to be taken with a grain of salt. Okay, so besides that, we also have two more data types that I want to talk about in this video. Everything else is going to be more complicated, but those are the primitive data types here. One is one that we already talked about, and this is the character, so the char, and this has usually 1 byte. Every other size is defined in terms of the char, so an integer has to have twice as many or 4 times as many as a character, a short has to have twice as many as a character, a long has to have 6 times what a character is, a long 8 times what a character is, and so on. So the character C is indicated here with single quotations, can be A, for example. A character C2, that's called a C1, can be also 30, so we can also store numbers in there. And then we can represent this in different ways. So I can say printf %d if I want to represent it as a number. So I can say %d \n C1. I can copy this and also represent C2. And you can see it works. Now this is the ASCII code of A. And what I can also do is I can represent this as a character. So I can say printf %c \n C1. And I can do the same thing with C2. And in this case, this is not a good character. Let's go with 90 maybe. Yeah, 90 is Z. So you can see that we can work with characters like that. Now what we can do here is we can say printf ld \n size of C1, for example. And you will see that it takes 1 byte. Now it's not guaranteed, but it's usually the case that a character has 1 byte. And we can also print the limit. So we can say printf max of character, and then as a number, character underscore max. And this is the maximum. Now, of course, we can also have an unsigned character. So if I say unsigned character, then probably I should change this to you. This did not work. Why didn't it work? Unsigned character max. Oh, because I'm printing the max, obviously. So actually, it doesn't make sense to make this unsigned in order to get a different result here. But the unsigned character can represent up until 255. And the last data type that I want to talk about is something that we know from other programming languages, but we don't have it by default in C, and this is the Boolean. We don't have the Boolean by default. If we want to use a Boolean, there are many ways. We have something like underscore bool. I think this is actually available by default even, but what I want to talk about is the std bool. So we can include here a library called stdbool.h, and this allows us to use a Boolean. So we can say bool b equals true, and then we can just print this. We can represent this as a number because that's fundamentally what it is. And true is going to be 1 and false is going to be 0. So if I do it like that, we get true. And if I do it like that, we get false. Now, I think we should also be able to assign 0. I'm not sure. We are. I'm not sure if we can assign a different number, though. Should be possible as well. Yeah. Okay, but we still get 1 because everything except for 0 is 1. So true. Yeah, we can also check the size here real quick. So we can say printf and then %ld \n size of b, and this is also 1 byte. So it's important to understand that this size off basically tells us how many characters this is. So if a character is 2 bytes instead of 1 byte, everything has to be multiplied by 2. By calling size off on an integer, we don't get the bytes, we get the units of characters. This is important. Yeah. So you might wonder where strings are. How do we represent strings? In C, it's not that simple because strings are essentially actually strings of characters, chains of characters. So this deserves a video on its own. Those are the primitive data types. We had integers, longs, short, long. We had floats, doubles. We can also have, I forgot to mention this, we can also have long doubles. I didn't mention that. Long doubles are, I think, how many bytes? What, 10 bytes? I think long doubles, let's try it out. LD equals whatever. I want to see if I print the size of LD is going to be actually LD itself. Size of LD. Let's see what we get here. I think it should be 10. It is 16. Okay, we have 16 bytes. This is a pretty high precision. Okay, so we have 16 bytes when we use long double. This is also a possibility. Then we also talked about characters. We talked about Booleans. Those are the primitive data types. And this is what we're going to build on top of. So that's it for today's video. Hope you enjoyed and hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe and hit the notification bell to not miss a single future video for free. Other than that, thank you very much for watching. See you in the next video, and bye.